Welcome to the 21st lecture on computational mathematics with SageMath. In previous lectures, we looked at finding derivatives and some of its applications. In next few lectures, we will look at dealing with integrals and its applications. So, suppose you have to find integration or integral of this kind. So, integral of cos x divided by square root of sin x plus 1 dx and integral of the same function from 0 to pi by 2. So, this is called indefinite integral, this is what is called definite integral. So, how does one find this in SageMath? So, first you need to define the function. So, the function I am calling as f(x) which is equal to cos x upon square root 1 plus sin x, and to find its integral, indefinite integral, you simply need to use f dot integrate or f dot integral with respect to the variable x. You could also use f dot integral, that will also work with respect to x. So, both gives you the same answer. Now, in case you want to find this second integral, that is definite integral, where the limit 0 to pi by 2, then you need to supply that limit after x you say comma 0 comma pi by 2. So, this is definite integral of the same function with limit going from 0 to pi by 2. Okay. So, this is 2 into square root 2 minus minus 2. If you want the numerical value, you can just say dot n, this will give you numerical value. Now, let us look at, suppose we need to find integral of this function. So, this is the integrand, and so this is square root of x plus square root of x square plus 1 divided by x dx, and its definite integral between 0 to 1 and 1 to 2. So, this is a fairly complicated function. If you try to do by hand, it may take some efforts. Now, let us see how Sage finds these integrals. So, let me again define this function f(x) is equal to square root of x plus square root of 1 plus square root x divided by x, and let us plot graph of this function. So, this is the function f of x and its graph. So, you can see here this graph near 0 it goes to a very high value, and when x increases this goes to close to 0, right. That is what you can see from this graph. But however, let us look at what happens to this between 0 and 1. So, again at 0, since the behavior is that it is going to increase to infinity. So, that is why you see this graph. Let me plot maybe between 0.1 and 1, then it may be somewhat better. Yeah, that's how the graph looks like between 0.1 and 1. If I say what is graph between 0 and let us say 1 and 2, or 1 and let us say 20, this became 120. So, this is the graph. So, you can see here this goes to very close to 0, right. So, now suppose if you want to find integral of this function, and let us ask it to show what is the integral value. The Sage is able to find integral, but this integral is given in terms of gamma function and f2 function, etc. So, this seems very complicated. I am not sure whether you will be able to make sense out of this, but let us see, suppose if I want to find out this integral between 1 and 2. So, this integral between 1 and 2, so Sage has an inbuilt function called numerical integral. So, this finds the integral numerically, and this will give you value of the integral along with error. So, in this case you can see here this integral is 1.2369, and whereas the error is 10 to the power minus 14. Whereas same thing if you try to find out integral between of the same function between 0 and 1. So, let us say take the numerical value of this. So, this is not actually numerical integration, it is finding the numerical integral, and it is finding in terms of hypergeometric function and gamma function. So, this is what is called hypergeometric function. So, if I say dot n, if I say dot n of this may give me the numerical value whatever it has found. It takes time because this function is fairly complicated. So, this is 2.72269, whereas if you apply numerical integral to the same function between 0 and 1 and then see what is that you are getting this. So, the integral is 69.98, whereas from this we got 2.72 and this is 69.99, whereas the error, this is the error term which is quite high. One cannot accept this kind of error in case of numerical computation. So, this is a very bad behavior in this case, but what I am trying to tell you with this example is that just do not believe whatever output that you get with any software. You should try to understand what is happening and then only you accept. Okay. So, it is very important to learn the concept and then use this kind of software to explore, right. So, yeah, so that is this we have already done, and similarly if you try to find, for example, integral of sin x by x between let us say 0 to 1. So, it gives you the value, this is the integral and this is the for example, error term. So, that is quite all right. If you try to look at this integral sin x upon x, this is actually a very important and famous integral, and this integral actually exists. This is one limit here is infinity. Such integrals are called improper integral. This one can find integral of this sin x upon x with respect to x from 0 to infinity. O means infinity, or you can write INFINITY, infinity, that also you can do. So, this is half into pi by 2, this is half pi by 2. So, if you look at what is the value of numerical value of pi by 2, then this gives you 1.5707, right. Whereas, if you try to find numerical integral using the same function between 0 to infinity. So, numerical integral will when we one wants to find the numerical integral, one has to divide the interval. In that case, the interval of infinite length will not be very convenient. So, in that case, that is why you can see here when you integrate this, now you are getting the answer which is 1.90, whereas this is actually answer, this is the correct answer, which is pi by 2, and in this case of course you can see here again the limit, the error term is very high, 1.698, almost quite close to 1.70, which is very high error. So, again when you want to compute numerical integral even with SageMath or that for that matter any other software of this kind, you should be careful. Okay. So, now the question is how does one find such an integral? For example, SageMath, how does it find this kind of integral? So, let us try to understand when we say integral of a function in an interval a to b, what it means is, for example, let us say integral of this function we want to find out between let us say minus 2 to 2, then what one means is that you have to find the area between this curve and x axis, area below this curve from minus 2 to 2. That's actually that you have to say signed area, because this side it will be negative. So, the integral can be negative, whereas area is always positive quantity. So, therefore, non-negative quantity, therefore, you signed area is nothing but the integral. So, that is what we need to do, right. So, if I look at if I try to shade this region, this is what this area of this signed area of this you need to find out. So, okay. So, for example, here this will be area under this curve this will be negative of the area under this curve, and when you add these two, this should give you the integral of this function from -2 to 2. So, from the knowledge of computing area from school, you know certain geometric figure and its area. So, for example, the way one has to calculate the area under this curve is by splitting this into area into some region whose area we know. So, for example, one of the thing we can do is we can try to approximate this area by means of rectangle. So, for that what one can do is one can divide this domain from -2 to 2 in equal parts, let us say n equal parts, and for each part, in each part try to draw a rectangle. So, for example, if I take between -2 and -1.5, so this is the region. So, you can approximate you can take the triangle by taking the left end point or from the right end point or the middle point, or for that matter any point as a height of that rectangle. So, let us see what I mean by that. So, for example, let me look at. So, suppose we divide this interval from -2 to 2 into, let us say, 10 equal sub intervals, and approximate this area under this by this rectangle, which is the height is taken as the left end point, value of the left end point. Everywhere the left end point is the height of the rectangle, and this is the width. So, if you try to approximate the integral using these sum of the area of this rectangle, you will see that this portion, this portion, this portion, this portion, these are the portions which are left out, whereas this is extra calculated. So, you expect that to have some error, whereas if you increase the number of the interval which you are dividing, at present we have taken 10, now suppose let me make it 30. So, when I make it 30, then the approximation will be much better, because now you can see here this the left out portion and the extra portion calculated, extra portion which are considered are very small. And if you take further more number of intervals or division, let us say if I take 100, then this will be very close to the actual area. So, that is one way to approximate this area. We can also use, instead of approximating area by taking the left end point as a height, we can take right end point. So, for example, let me just do it for the 10 sub intervals, right end point. So, for example, here this is the height, here this is the height, the right end point, this is the height, here this is the height, this is right end point. So, this is the height, and so on. So, that is a one calls this as right Riemann sum, and you can also take midpoint. For example, if I take r is equal to 0.5, then it will give you the rectangle which is whose height is the value of the function at the midpoint of this each of this interval. So, this is what is called midpoint Riemann sum. So, and as you increase the number of the sub intervals, number of points inside this sub interval, then you will get actual close to the area, right. So, let us say you can also, in order to define this integral which is called Riemann integral. So, what we are doing, we are approximating integral of f(x) from a to b by means of this sum of the area of this rectangle, where f(x) star is the height and this is the width. Now, width is, if you are dividing the interval into n equal parts, the width is b minus a by n, and this is the height. So, this is the formula, right. Now, in case of lower end point, left end point, x k star is x k minus 1, and in case of right end point you have to take x k. In case of midpoint you take x k plus x k minus 1 by 2, but in principle one can take any point in between and do this calculation. Generally, in case of Riemann integral, one takes this x star, one takes as the point at which the minimum occurs, and also the points at which the maximum occurs. These are called lower Riemann sum and upper Riemann sum, and then one has to take what is called infimum and supremum and infimum of these two sums. Okay. So, here x k is a plus k into b minus a by n, and k will take value 0 to n. For example, k equal to 0, if k equal to 0 you are at a, if k is equal to n you are at b, and so on, right. So, if you try to see what is the approximate area when you take the left endpoint, and let us take this division as 20, or let us say 20, divide this area this interval into 20 equal parts, then the value of the actual integral which is calculated using Sage, it is -4, whereas this approximate area is -3.6. So, as you increase, when you increase this interval, let us say make it 50, if you make it 50, then it will is -3.84, which is somewhat closer to this, and if you increase further, let us say make it 100, then you will get much closer. So, in this case you have this approximate area is -3.92, whereas actual is -4.0. So, and so on, and you could do it with left endpoint, right endpoint. So, in this case if I make r is equal to 1, this will use right endpoint. So, this is the right endpoint. You can see here if you take the right endpoint, the area approximate area is somewhat more than the actual area, little bit more, right. So, this code you can for example look at, this is fairly simple. What we are doing is we are taking a is equal, this is the function, a and b are the endpoints, n is the number of intervals, r decides whether you want to take left endpoint or right endpoint or midpoint. So, that is the, so accordingly you calculate the delta. So, delta is the length of each of this interval, and r delta is r times delta. So, it will, if r is equal to 0, it will take the left endpoint, if r is equal to 1, it will take right endpoint, if r is equal to 0.5, it will take the midpoint, and then x k is the a k is stored in x k here. Initially x k is a, and then this is the set of all the points, because you need to plot these rectangles. So, these rectangles, the way you need to store these rectangles, let me just first make it small interval, let us say 10. The way you need to plot these rectangles is first you plot, let us say this point, then plot this point, then plot this point, then this point, and then you again go to this point, and then you go to the next point, and like this. So, you add all these rectangles vertices together, and then at the end you have to also add this end point here, this 2, 0 in this case, and then you plot this using what is called polygon plot. So, using polygon plot you plot this, and this is the graph of the function, and then you are filling this graph under between the function and the x axis, and here s is calculated as the Riemann sum. So, at each point you can see here s is equal to s plus y, y is the value of the function which is the height, and then you keep on adding the height, and then at the end s is multiplied by the width of each interval, right. So, you can also create animation for this using Sage interact function. You can also create user defined function for left Riemann sum. This is quite simple. Similarly, for right Riemann sum and midpoint Riemann sum. So, if it is left Riemann sum, you supply the value of the function f, the endpoints a and b, and the number of intervals, and this is the delta, and then you are for each thing you are calculating the height, and then ultimate at the end you multiply by the length of each interval, right. So, if you take for example x square, the function f of x equal to x square, and try to find this left Riemann sum, this is 2.66, the integral of x square will be x cube by 3, So, at 0 to 2, that is 8 by 3, which is quite close to 2.6666, right. Similarly, if you take the lower right Riemann sum, then you just need to define this as x plus delta into I plus 1, and again you can call this let us say instead of 2000, let me just have 200 points. Yeah, so this is also very close to this. Similarly, the mid point rule, and you can call this function again, let me call only with 200 points. So, that is the, so this is mid point rule will be much closer to the actual value, right. So, this is how you can approximate the integral from a to b of f(x) dx. Now, but in actual practice, in order to define the integral, this I will skip, because this is all you need to do is just put add the rate interact and put all the codes that we have seen earlier. This will create a animation where you can change the function, you can change the a and b, you can change the number of points, all these things will be interactive, right. The way one defines the Riemann integral, as I said earlier, is that instead of left and right endpoint, you just take f of x tk star, where tk star is the point at which the function has minimum in the interval xk minus 1 to xk, and where you take a partition p is any partition of this interval a to b. This should have been xn to b, just one second, this should be b, this is b. So, you take any partition and then define what is called lower Riemann sum. Similarly, instead of tk star, if you take the point where the maximum of the function occurs, and this maximum and minimum will occur because we are assuming considering f to be bounded. For existence of integral, we assume that f is bounded on the interval a b, and so you consider this u l f p and u f p for each of this partition, and take all such left Riemann sum and right Riemann sum for all the possible partition set of all partition, and then you define what is called supremum for LF. One can show that these supremum exist because this will be bounded above by b minus m b minus a by into the maximum value of the function in the interval a b, and similarly this will be lower bounded below. So, it will have supremum and LFP and UFP will have infimum. So, you find out the infimum and supremum of these two. In case these two supremum and infimum, which we are calling as LF and UF, if they agree to each other, they are the same, then we say that f is Riemann integrable, and the value of the Riemann integral is a to b f(x) dx. That is the notation, the Riemann integral. This is how we denote, right. So, this was given by Riemann, that is why it is called Riemann integral. And this but the here problem is that to find this x tk star and f xk star will be somewhat tedious process, but in case the integral exists, then you can divide this interval into let us say n equal parts, and you take n very large, then the value of this Riemann sum will be close to actual integral. So, that is how one defines Riemann integral of a function, right. Next, let us look at the fundamental theorem of integral calculus. The integral which we find actually based on these two fundamental theorem. So, it says that in case the function is differentiable and at the same time f dash is integrable, Riemann integrable, then integral of f dash x dx from a to b will be nothing but fb minus fa. So, that is how you find the integral. So, in order to find this integral, you need of a function, you need to find the function whose derivative is the actual function, and then you take the difference of the function derivative of that function whose derivative is the integrand, then you look at the difference. Similarly, if you define, let us say if the function is integrable, you define integral of f t from a to x dx, sorry, it should be dt here, this should be dt because that is the variable with respect to we are integrating. So, this is a function of x. So, what actually we are doing, we are taking any x and we are finding the area under this curve f t from a to x, and one can show that this function f x this function f x, which is called antiderivative or indefinite integral of f, this will be differentiable in case f is small f is continuous at x, then capital F will be differentiable at x, and not only that, the derivative of f of capital F x is small f x. So, that is what is called second fundamental theorem of calculus. So, if you define this indefinite integral of f, take the derivative, that is what you get, capital F dash x is small f x. So, this is called second fundamental theorem of integral calculus, this is called first fundamental theorem of integral calculus, and this calculation of this Riemann integral is actually based on these two facts, right. So, let us look at a small example. Suppose I have a function f t is equal to t square, and if I find the integral from t to x, I call this as capital F x, and if I look at what is the graph of this function capital F x along with the graph of a small f x, then this is how you see. This is a red curve is graph of f x and the blue one is graph of derivative graph of this indefinite integral of small f, and you can see this is the parabola x, the graph we have taken is f x equal to x square, and this is what you are getting is cubic. So, if I try to find the derivative, of capital F x with respect to x, you should get x square, that is what you get, right. Similarly, you can take another example, this is somewhat more complicated. F of x is equal to f of x is equal to x into e to the power 2x, and let us define this indefinite integral as g x from 1 to x, and then find what is derivative of g at 1. So, this is again very simple. So, define t and x as variables, define g of x as indefinite integral, and then find the derivative of g, let me call this as g1, and evaluate g1 at 1, which is e to the power 2, right. So, that is a verification of this fundamental theorem of integral calculus. Now, suppose you need to define, for example, integral of tan x square from 0 to 1. Okay. So, again you can find out this integral using integral, but in this case you see that this does not give you the integral, it simply returns whatever you have written. So, that means this integral Sage is unable to find this integral in closed form. So, in that case what you can do is you can find the numerical integral. So, if you say this n will not work, so what it says is this is not callable. So, you need to find this as numerical integral. In this case you will get the value. So, if you in this case numerical integral is 0.3984 and with error of the order 10 to the power minus 15, right. So, many times if you have the definite integral, it is the Sage may not be able to find in closed form, and therefore, in that case you need to find numerical integral, right. Similarly, let us take another example. So, suppose you have function f t is equal to t minus t square, and define this antiderivative capital F x is equal to 0 to x f t dt, and find the positive value of x such that capital F x starts decreasing, that is the problem. So, it is quite simple. So, first let us plot graph of the function f and graph of indefinite integral capital F x, and then see what happens. So, this is the graph of the function capital F, and you can see here when it is going to capital F, this is graph of capital F, and when does it start decreasing. So, you can see here this is the point when it starts decreasing, and so let us look at suppose we we plot also the graph of the function. This should be, let us plot this small f and capital F together, so that we can compare. Right, let me put this in red color equal to red. Right. So, the blue one is graph of the function, and the red one is graph of indefinite integral capital F x. So, you can see here this at this point small f goes to negative. So, here the before that this indefinite integral, that is area capital F x will start will go on increasing, whereas the moment the function becomes negative, then the capital F x will start decreasing. So, that is the point. Okay. Right. So, here the point is sorry, not 1 point, it is at 1. At 1 the capital F x will start decreasing. Right. Okay. Let me. So, we saw that some integral does not have closed form antiderivative. In that case, you need to find numerical integral. Similarly, if you try to find out, for example, the integral of sin x square, again this integral of sin x square gives you something in terms of ERF, that is called error function, and this error function is defined as ERF x is equal to 2 upon square root pi integral from of e to the power minus t square 0 to x square. Those who have done a bit of statistics would be aware about this function. So, this integral is given in this error form. Of course, you can find what is integral of e to the power minus x square with respect to x, that is so it will be error function times square root pi by 2. So, that this scaling factor is coming here, and if you want to find integral of such function, so for example, integral of sin x upon x, this gives you in terms of EI of I of x. Again, you can look at what is this EI function. So, many times the integral of some of the standard function is defined in terms of some other function, either error function or EIX. So, these you can find numerical values of these things. For example, here in this case I can say dot n, it is not giving, we have seen already because this is the indefinite integral. So, dot n does not make sense, whereas if I put this limit 0 to, for example, infinity, then this integral is pi by 2. Right. Okay. So, let me leave you some easy exercises. These are some easy exercises of computing definite and indefinite integrals, along with some of them are quite straightforward, some of them are not so straightforward when it comes to calculating by hand. And the last problem is that if you look at this sin of x square, we saw that this integral is not in closed form, but you just find out left and right Riemann sum. We have already defined what is the function and tabulate this value between for n is equal to 10, 20, 30, 50, 80, 100. This is just to demonstrate that this integral will actually converge to the actual integral. So, okay. So, thank you very much. We will look at some more examples in the next class.